Japan 1944. Over the vast Pacific, the night sky flickered with the hum of distant engines. Japanese radar operators, weary from months of bombing raids, scanned their green glowing screens, eyes fixed on the sweep of light that revealed the unseen. But tonight, something was different. A group of incoming aircraft had been detected earlier, B-29 bombers, massive and methodical. Yet now, the radar scopes began to flicker and fade. Blips that once pulsed clearly across the display vanished. The operators hit the panels, checked the circuits, but the screens stayed blank. Interference? One asked. Impossible, replied another. There's no storm tonight. Moments later, explosions lit the horizon. The bombers had struck their targets, undetected, unhindered, and almost invisible. Across Japan's air defense network, confusion spread. It wasn't just one radar, it was all of them, from Kyushu to Honshu. Every early warning station reported the same thing: strange static, distorted echoes. Some even said it sounded like laughter in the frequencies, a pulsing rhythm that mocked every effort to track the enemy. At Yokosuka Naval Headquarters, an urgent message was transmitted up the chain. Unidentified electronic disturbance detected, believed to be caused by new American equipment. Immediate investigation required. And so, for the first time, Japan realized it wasn't just fighting a war of steel and fire, but a war of signals and silence. By mid-1944, Japan's technological edge had eroded. Radar, once a rare secret, had become a decisive weapon of the modern battlefield. While Japan had made progress with its own radar systems, the Type II and Type III models, American engineers had already moved to the next frontier: electronic countermeasures. To most Japanese officers, the idea of jamming radar seemed absurd. Why spend precious resources to disturb radio waves when you could build more planes or guns? But in American laboratories, from Harvard's Radio Research Division to Bell Labs in New Jersey, scientists were exploring the invisible battlefield. They called it electronic warfare. And now, for the first time, Japan was feeling its effects. In the smoldering ruins of an airbase near Kagoshima, a Japanese recovery team moved among the debris of a downed bomber. The wreckage was twisted beyond recognition. The giant four-engine aircraft had crashed after taking heavy flak. Among the burnt-out pieces of metal, a young engineer spotted something unusual: a rectangular box, dented but intact, painted in dull gray, with English markings and small tubes protruding from its sides. He wiped off the soot and stared at the stenciled letters. U.S. Army Signal Corps, property of the United States. The officer in charge barked an order: "Send that to Yokosuka, immediately." None of them knew it then, but that strange box would lead to one of the most shocking realizations of the entire Pacific War. In the months to come, Japan's brightest engineers would take that captured device apart, piece by piece, wire by wire, trying to understand how it worked. And when they finally did, they would discover something that would shake them to their core. Because inside that metal box wasn't just a weapon, it was proof that America's technology was decades ahead. Yokosuka Naval Arsenal, early September 1944. The air smelled of oil and damp metal, the rhythmic pounding of hammers echoing across the massive shipyard. Within one of the smaller research hangars, a place normally used to test naval electronics, a group of engineers gathered around a workbench. At the center lay the captured American device, still charred from the crash. The man overseeing the inspection was Commander Hiroshi Nakamura, a 38-year-old electrical engineer educated at the University of Tokyo. Before the war, Nakamura had worked on Japan's early radar experiments, the Type I Model I air search radar used on Japanese battleships. But even for him, this new artifact was something else entirely. "It's compact," he murmured, turning the metal casing over with his gloved hands, "and modular, almost like it was built for easy replacement." He paused. "The Americans don't just build strong machines. They build them to adapt." For days, the team documented every component inside. The small vacuum tubes, resistors, and tuned circuits were familiar in principle, but the configuration was alien. The most unusual part was a panel labeled an APT-1, and below it, in faint lettering, Radio Countermeasure Unit, U.S. Army Signal Corps, 1943. Nakamura and his assistant, Lieutenant Akira Fujimoto, exchanged a glance. They'd heard rumors from intercepted American communications about something called carpet jamming. Could this be it? What they had found was, indeed, one of the most advanced pieces of airborne electronic warfare at the time, the APT-1, part of a family of radar jammers designed to interfere with enemy detection systems. The device emitted bursts of radio noise precisely tuned to the frequency of Japanese early warning radars. To the radar operator, it looked as though the screen had filled with false echoes, waves of static that blinded their ability to track real aircraft. In the simplest sense, it turned Japan's eyes blind. "Commander," said Fujimoto, holding a notepad, "these tubes here, they generate wideband noise across multiple frequencies. It's no wonder our Type 2 radar lost the signal." Nakamura nodded, still studying the circuitry. "They've built an automatic tuning. It adjusts itself mid-flight." He frowned. "We can't even do that on the ground." The room fell silent for a moment. Only the faint hum of a generator filled the air. "Fujimoto," he finally said, "this isn't just an invention. It's a philosophy, sir. They're not just trying to build better weapons. They're trying to control information itself." At that moment, Nakamura understood something that few Japanese officers yet realized, that the war's next frontier wouldn't be decided by steel or gunpowder, but by who could manipulate the invisible spectrum, radar, radio, frequency. Those were the new battlefields. But Japan was already too far behind. A small conference room inside the Naval Ministry headquarters. Present were high-ranking officers from the Imperial Navy's Technical Division, including Rear Admiral Yasuo Abe, head of Japan's radar development program. On the table, technical sketches, notes translated from English, and a disassembled panel of the APT-1 jammer. Nakamura gave his report. He explained how the device detected enemy radar signals and emitted disruptive noise at the same frequency, a process that required advanced oscillators, amplifiers, and automatic gain control systems far beyond Japan's capacity to mass produce. "In short," he said quietly, "the Americans can render our radar ineffective at will." The room went still. No one spoke for nearly 30 seconds. Then Admiral Abe finally asked, "Can we replicate it?" Nakamura hesitated. "With time, yes. But by the time we do, they'll already be years ahead." Outside, the sound of distant air raid sirens echoed across Tokyo. For the engineers inside that room, the irony wasn't lost. They were listening to the same alarm system that the Americans could now turn blind at any time, any night, anywhere over Japan. And yet, amid the despair, Nakamura made a decision that would change everything. He ordered the construction of a reverse-engineered prototype, one that could, in theory, detect and jam allied radar frequencies. They called it Project Keishin, the signal of the rising sun. Winter 1944. Japan's once mighty industrial engine was faltering. Fuel was scarce. Aluminum was rationed. Entire factories stood silent after Allied bombing raids. Yet in a small, heavily guarded laboratory inside the Naval Technical Research Institute in Tokyo, a group of engineers worked in near total secrecy. Their mission: to replicate the captured American radar jamming device and somehow make it usable with the limited components Japan still possessed. They called their endeavor Project Keishin, the signal that rises with the sun. The lab was dimly lit, its air thick with cigarette smoke and the faint buzz of generators. Commander Hiroshi Nakamura stood over a table scattered with tools, wires, and fragments of the American and APT-1 unit. Beside him were two key figures: Lieutenant Akira Fujimoto, his loyal assistant and translator of technical documents, Dr. Kenji Matsuda, a physicist formerly employed at the Institute of Physical and Chemical Research Riken. "Commander," Fujimoto said quietly, "if we substitute these American resistors with our local stock, the signal strength drops by almost half. Then boost the output tube," Nakamura replied. "We can't. The cathodes overheat." Dr. Matsuda set his pipe down. "Our material science simply isn't ready for this," he muttered. "Their components use alloys we don't even have names for." Nakamura exhaled slowly, his patience thin but his resolve unbroken. "Then we'll name them," he said, "even if it takes us till the end of this war." Japan's wartime electronics programs had produced radar sets such as the Type II Mark II Model I and experimental detection systems aboard ships and planes. But in comparison to Allied technology, they were crude, using hand-tuned components, often built by untrained laborers. The Americans, aided by British and Canadian research, had already deployed radar countermeasures like window chaff and jammers operating across entire frequency bands. By late 1944, Japan's electronic warfare capabilities lagged behind by nearly 4 years, an eternity in the fast-evolving world of wartime science. The next evening, tensions rose. The prototype, a crude frame of copper wiring and mismatched tubes, failed yet another test. A faint whine filled the lab, followed by a pop and a wisp of smoke. "It's not holding frequency," Fujimoto said, covering his face. "It keeps drifting." "Of course it does," Matsuda replied bitterly. "Their circuits are stabilized by temperature-compensated capacitors." "We have paper and wax enough," Nakamura said sharply. "We can fix the drift manually." He turned to Fujimoto. "Bring me the oscilloscope. We'll tune it by hand." Hours passed. The room grew cold, their breath visible in the winter air. But by dawn, a faint pattern appeared on the radar receiver across the room. A wave of interference, imperfect, but present. "There," Nakamura whispered. "It's weak, but it's working." For a moment, no one spoke. Then Matsuda finally nodded. "You've done it, Commander." Nakamura looked at the flickering signal, knowing it was only a shadow of what the Americans had built. Yet even a shadow meant hope. In the months that followed, the Keishin team refined their design. Each test brought new failures, but also new insights into how far Japan's technology had fallen behind. The more they learned about the American device, the more they realized they were not fighting just a war of armies and ships, but a war of information. Rear Admiral Yasuo Abe sat across from Nakamura in a bomb-damaged conference room. Tokyo was in ruins. Allied bombers roamed freely overhead. Nakamura presented the latest prototype, compact, wired, functional. "We can jam at least one radar frequency reliably," he explained, "for a few minutes at a time." "That's not enough," the Admiral said flatly. "It's the best we can do with what we have left." Abe nodded slowly. "And if it fails, then we learn from that failure, sir." Just as they learned from ours, there was a silence between them, one that carried the weight of a dying empire. By the time the first Keishin prototypes were ready for field testing, the war was already entering its final, desperate phase. Fuel shortages grounded most aircraft. Factories once meant for innovation now struggled just to rebuild what had been bombed the night before. And yet, even as the empire collapsed around them, a handful of engineers kept working in that small, secret lab, not for victory, but for understanding. They wanted to know how the Americans had mastered something so invisible, so powerful, because in that knowledge, they saw the shape of the future. The last entry in Nakamura's notebook, dated July 28, 1945, reads, "We are surrounded by ruins, but I feel no despair. For even in defeat, knowledge endures." That was the legacy of Project Keishin, a desperate attempt to bridge a technological abyss, a final act of curiosity in the midst of destruction. Summer 1945. The sound of sirens had become the soundtrack of Tokyo. Every day, American B-29s rumbled overhead, leaving trails of fire and smoke that painted the city in shades of gray and orange. Inside the Naval Technical Research Institute, Commander Hiroshi Nakamura and his dwindling team continued their work in near silence. Food was scarce, power was unreliable, and yet, amid the ruins, the lights in their labs still burned. "We're scientists," Nakamura told them. "Even if the war ends, our duty is to learn what we can." While we still can, outside, the empire was falling apart, but inside that room, their focus remained absolute. A final prototype sat on the bench, scarred, imperfect, but functioning. It hummed with a faint electric pulse, the same tone they had come to recognize after months of failure and progress. Dr. Matsuda leaned over the unit, adjusting the dials. "The modulation's stable," he said. "Better than before." "Good," Nakamura replied. "Let's see if it can hold the frequency." Across the room, Fujimoto adjusted the radar receiver. For a moment, static filled the air. Then a burst of jamming appeared, clear and sharp. "It's consistent," Matsuda said in disbelief. "Commander, this is the first time it hasn't drifted." Nakamura didn't smile. He simply stared at the readings, calm, proud, but weary. "Then we've done it," he said quietly. "Too late, but we've done it." By early August 1945, Japan's war was effectively over. Industrial production had collapsed. The American Navy had full radar coverage across the Pacific, and the skies belonged entirely to the Allied air forces. Japan's radar countermeasure research, including Project Keishin, would never seek combat deployment, but its data, stored in coded notebooks and technical schematics, would soon become one of the most valuable post-war discoveries of all. The engineers gathered around a small wooden radio in the lab. The voice that came through was faint, formal, and broken by static, but unmistakably, it was Emperor Hirohito. He spoke of enduring the unendurable and bearing the unbearable. When the broadcast ended, no one said a word. Dr. Matsuda removed his glasses and placed them on the table. "So, this is it." Fujimoto sat down heavily. "All this work, all these nights, for nothing." Nakamura shook his head. "Not for nothing," he said. "We've glimpsed the future, and it belongs to those who understand what they build." In the weeks that followed Japan's surrender, Allied forces began sweeping through research facilities across the country, collecting blueprints, notes, and prototypes. At the Naval Technical Research Institute, American officers found the remains of Project Keishin, a partially assembled jammer, a few burnt-out tubes, and notebooks filled with detailed analysis of American technology. Among them was a hand-drawn schematic labeled U.S. Radar Countermeasure, Function, Signal Masking through Frequency Modulation. The Americans immediately recognized it. It was a near-perfect understanding of their own APT-1 carpet jamming system, reverse-engineered by hand, under wartime conditions, with almost no resources. Major Robert Ellis, an Army Signal Corps officer, examined the device inside a makeshift inspection tent near Yokosuka. He turned to his interpreter. "Whoever built this," Ellis said, "knew exactly what they were looking at." The Japanese officer beside him replied quietly, "They studied it for almost a year, sir." Even when the bombs were falling, Ellis nodded, impressed. "They were behind us, but not by much." After the war, many of Japan's top scientists were quietly recruited by Allied research missions. Their knowledge of materials, aerodynamics, and radio technology was invaluable in the early years of the Cold War. Some of the men from Project Keishin, including Dr. Kenji Matsuda, would go on to work in post-war communications and radar industries, laying the groundwork for Japan's eventual transformation into a world leader in electronics. Commander Nakamura's fate, however, remains uncertain. His name appears briefly in occupation records from 1946 and then disappears entirely. Some say he was detained. Others believe he continued working anonymously for the new government. But his notebooks, the heart of Project Keishin, survived. Tokyo, 1952. A group of young engineers at a small electronics company flipped through those same notebooks. On the final page was a note in fading ink. "One day, we will build devices not for war, but to connect the world. Those words inspired a generation of post-war innovators, men who would build the radios, televisions, and transmitters that defined Japan's technological rebirth. Project Keishin was never completed. It never flew, never jammed a single radar. But in its failure, it became something greater, proof that even in defeat, the pursuit of understanding could transcend war. When the Japanese engineers studied America's radar jamming device, they realized they were not just looking at a weapon. They were looking at the future of communication itself. Autumn 1945, Japan had surrendered. The war was over, but the work of understanding why it ended the way it did had just begun. Across the Pacific, teams of American engineers, scientists, and intelligence officers were deployed to Japan. Their mission was clear: find what they built, find what they studied, and find out how close they came. This operation would become one of the most extensive scientific investigations of the 20th century. The Technical Intelligence Program, led by the U.S. Navy and Army Signal Corps, and among their findings, one discovery stood out: a mysterious device labeled only as Project Keishin. Inside a half-destroyed lecture hall, American technicians unpacked crates of confiscated Japanese research materials. Among the folders were hand-drawn schematics, frequency charts, and signal records, all meticulously labeled in Japanese. Major Robert Ellis, the same officer who had inspected the prototype earlier that year, now led a small analysis team. He placed a tattered binder on the table. "Gentlemen," he said, "this is the one they called Keishin." Lieutenant James Reynolds, a young radar expert from MIT, flipped through the documents. Even from a glance, he recognized the patterns. "These are harmonic frequency modulations," Reynolds said. "They're mapping the exact bandwidth of our B-29 jammers." Ellis nodded. "That's what I thought. But they didn't just copy it. They improved the tuning circuit." For a moment, the room went silent. Reynolds leaned back in his chair. How the hell did they figure that out? What the Americans discovered was shocking. Despite severe material shortages, Japan's engineers had achieved a near-complete understanding of American radar jamming technology, including the APT-1 Carpet and an APT-3 Jackal systems. They had mapped signal strengths, analyzed harmonics, and even created miniature test transmitters to simulate radar lock-on effects. In essence, the Japanese scientists had been performing reverse engineering, not through captured blueprints or leaks, but through sheer observation, physics, and determination. The report compiled by Major Ellis's team was stamped confidential. It contained a single line that stood out among dozens of technical paragraphs. Given 6 additional months of stable production, Japan may have successfully deployed radar countermeasures capable of limiting Allied bombing efficiency. That line alone sent ripples through the intelligence community. At the Signal Corps' headquarters in Washington, D.C., analysts debated the implications. How had a nation so battered and blockaded come so close to breaking one of America's most advanced wartime technologies? The answer lay in the sheer ingenuity of Japan's wartime engineers. Working under relentless air raids, shortages, and censorship, they had developed systems parallel to Allied research, not as effective, but conceptually similar. Their understanding of frequency modulation, pulse delay, and signal scattering was decades ahead of what American scientists had expected. The U.S. had underestimated their capacity to innovate under pressure. In an interview recorded by U.S. intelligence officers, Dr. Kenji Matsuda, one of the Project Keishin scientists, described his motivations. "We did not work out of loyalty alone," he said quietly. "We worked because the challenge was greater than the war itself. To capture the invisible, that was our mission." When asked what he meant by invisible, Matsuda smiled faintly. "Radio waves, the unseen battlefield." For the Americans, Matsuda's words resonated. The unseen battlefield, that phrase would echo in the early Cold War years when radar, signal intelligence, and electronic warfare would become the backbone of modern defense. Many of the techniques studied in Japan especially those concerning signal masking and pulse interference, would later appear in U.S. research programs, subtly credited under the vague term foreign technology influence. Inside the newly formed Air Force Technical Intelligence Center, Major Ellis presented his findings. A series of black and white slides flickered across the screen. Grainy photos of the Project Keishin device, Japanese blueprints, and lab notes. "We expected primitive systems," Ellis told the panel. "What we found instead was a structured research effort, disciplined, methodical, and in many cases, conceptually advanced." One general leaned forward. "You're saying they were close?" Ellis replied, "Closer than anyone wants to admit." In that moment, the myth of Japan's purely mechanical wartime industry began to fade. The Allies realized that beneath the chaos of total war, Japan had harbored a deep, scientific understanding of modern electronics, a foundation that would soon power its economic miracle. And for the men who had worked on Project Keishin, their wartime failure became a post-war legacy. Years later, in 1963, when Japan launched its first domestic communications satellite test, a small brass plaque was placed inside the engineering division's lobby. It bore no company name, no logo, only a single inscription, dedicated to those who studied the unseen. It was said to have been commissioned by Dr. Kenji Matsuda himself, a quiet tribute to the men who once tried to block radar waves and ended up shaping a nation's technological destiny. When Japanese engineers examined America's radar jamming device, they did more than decode a weapon. They glimpsed a world beyond war, a future where mastery over invisible waves would unite rather than divide. And in that silent exchange between defeated scientists and their conquerors, the future of global communication quietly began. The war was over, but the lessons it left behind were only beginning to surface. In laboratories from Tokyo to Washington, the discoveries of World War II, radar, jamming, encryption, and atomic science were being reshaped for a new age. The world had entered a different kind of conflict, one not fought with tanks or rifles, but with information, signals, and silence. This was the dawn of the invisible war. The ghosts of innovation naval labs that once tested radar jammers now produced radio transmitters for civilian use. The same men who once hid their experiments from Allied bombers now worked under fluorescent lights, designing circuits for public broadcasting. Dr. Kenji Matsuda, the last surviving senior member of Project Keishin, took a teaching post at the University of Tokyo each semester. He opened his first lecture with the same sentence, "War taught us how to listen. Peace will teach us how to understand." Students adored him. He rarely mentioned the war, but occasionally his gaze lingered on the old cathode tubes he kept on his desk, silent relics of an age when failure meant survival. The American continuation in the United States. The files from Japan's research were quietly integrated into new military programs. The carpet and jackal jammers evolved into more advanced systems like QRC-279, later used in the Korean War. Engineers at Bell Labs and MIT's Radiation Laboratory drew heavily from foreign data, including Project Keishin's signal masking principles. Few knew their origins. Fewer still cared. To them, it was simply data recovered from enemy facilities. But in technical reports filed years later, references to parallel Japanese developments began to appear, a subtle acknowledgment of respect. They were working in darkness, one engineer wrote, and yet they reached for the same light. The race for the invisible. By the mid-1950s, the world had split into technological empires, East and West, both racing to master the unseen. Satellites, radar arrays, and early warning systems filled the skies. The principles of jamming had now transformed into something grander, electronic warfare. The science of controlling information itself. The same mathematics that once disrupted radar now guided the first modems. The same pulse delays that once hid aircraft now carried voices across oceans. The line between war and progress had blurred completely. A quiet visit. It was a warm autumn evening when an American visitor arrived at the University of Tokyo. His name was Robert Ellis, the retired major who had once examined the captured jamming device 19 years earlier. He requested a meeting with Dr. Matsuda. The two men, now gray-haired and slow-spoken, met in a small faculty lounge overlooking the campus. For several minutes, neither spoke. Then Ellis reached into his coat pocket and placed something on the table, a small metal plate, polished but scratched, engraved with Japanese characters. Matsuda froze. It was the identification tag from the original Keishin prototype. "We kept it," Ellis said quietly. "I thought it should come home." Matsuda smiled faintly. "It never belonged to any side," he replied. "Only to the idea." They spent the next 2 hours talking, not about nations or armies, but about wavelengths, interference, and the beauty of precision. Two former enemies, united by curiosity. When Ellis stood to leave, Matsuda extended his hand. "Perhaps," he said, "we were never fighting each other. Only time." The silent inheritance collaboration between former wartime scientists continued quietly through the 1960s. Joint research programs, exchange lectures, and technology transfers blurred the lines between victor and vanquished. In 1967, a small radar signal conference in Geneva brought together engineers from 12 countries, among them Dr. Matsuda's protege and a former U.S. Signal Corps researcher. During the final session, one presenter quoted an anonymous note found in post-war archives: "The invisible is not our enemy. It is our final frontier." The audience applauded, not for the author, who remained unnamed, but for the truth of the words themselves, the legacy remembered for decades after the war. A Japanese television crew filmed a documentary about the nation's forgotten scientists. In one scene, they visited a warehouse outside Yokosuka where dusty equipment still sat on wooden crates. Vacuum tubes, oscilloscopes, and one rusted chassis marked Keishin Type 1. The narrator's voice trembled as he read the inscription on its side: "Prototype, never tested." For a moment, the camera lingered on the machine, silent yet defiant, a monument to human perseverance. Reflection: the true meaning of progress. History often remembers wars through battles, generals, and victories. But true progress rarely begins on the battlefield. Sometimes it begins in a dimly lit workshop, with a handful of tired engineers chasing the faint hum of a signal they cannot yet control. Project Keishin was born in secrecy and ended in silence. Yet from its ashes rose an idea that transcended nations, that knowledge itself cannot be conquered. The same frequencies once used to deceive now carry information, music, and hope across continents. The same spirit of discovery that once built weapons now builds connections. Epilogue: the signal that never died in a museum tucked behind the National Science Center in Tokyo. A single exhibit glows softly under glass. It's a small metal device, rectangular, with fading kanji etched on its side. Next to it, a caption reads, "Radar Countermeasure Unit, recovered 1945. Symbol of technological transition." Visitors rarely stop for long. To most, it's just another artifact. But for those who understand, it represents something far greater. The moment when science looked past destruction and found creation. When Japanese engineers examined America's radar jamming device, they didn't just uncover the mechanics of an enemy weapon. They uncovered a truth as old as civilization itself. Innovation is not born from power. It is born from understanding. From the ashes of war, the frequencies of peace emerged, and with them, the invisible threads that now connect every corner of our world. By the spring of 1944, the Imperial Japanese Navy's Radar Research Bureau, under Rear Admiral Yajima Takashiro, began producing early prototypes, inspired by what they believed the captured American device was doing. They called it Type 6 Denpa Kagyuki, literally, wave interference apparatus. But there was one problem. No matter how closely they followed the circuitry, the device didn't jam radar directly. Instead, when tested at the Tateyama Naval Communications Center, it produced strange, flickering echoes, false ghosts on the radar scope that came and went unpredictably. The engineers realized this was not a malfunction. It was intentional. The American device didn't blind enemy radar. It deceived it. It could make aircraft appear where none existed. Entire bomber squadrons could be masked by false returns. The report, written by Lieutenant Commander Takashi Kawaguchi in June 1944, read, "This is not a mere jammer. It is a ghost maker, a device capable of painting illusions upon the enemy's screens." Japanese scientists, now working under intense pressure from the Ministry of Munitions, struggled to reproduce the stability and precision of the American circuits. They discovered the key component, a small quartz crystal oscillator paired with a precision variable capacitor, allowed the signal to fluctuate in a narrow, tunable band that created a false radar echo. In modern terms, it was an early form of electronic countermeasure (ECM) deception. But to them, it was magic. By late 1944, the engineers at the Kogane Technical Institute were desperate. Japan's skies were dominated by American B-29 bombers. Tokyo, Nagoya, and Osaka were being incinerated night after night. The captured radar jamming device, once a curiosity, became their last hope. They tested their first field unit aboard a Kawanishi H-8K Emily flying boat over the Philippine Sea. The pilot reported that American radar detection seemed to lose lock intermittently, the first success. But the power requirements and the instability of their reproduction made it impossible to deploy at scale. And so the project was shelved. But the reports, all 182 pages, survived, hidden in Tokyo's technical archives until 1949. Years later, when American engineers reviewed these documents, they were stunned. The Japanese had discovered, almost independently, the principle of chaff interference and electronic deception, a technology the U.S. would later refine into modern radar stealth and ECM systems. When the war ended in August 1945, Japan's research centers became silent overnight. Bombed-out laboratories, half-finished prototypes, and burned documents marked the collapse of what had once been one of the most advanced scientific networks in Asia. But a few records survived, hidden in sealed vaults, mislabeled storage rooms, or private safes of officers who had refused to destroy everything. Among them, a set of brown folders marked D-104, American Device Analysis. In 1946, U.S. occupation forces, specifically the Technical Intelligence Division TID, began combing through Japan's remaining research materials. Their mission was to locate any surviving data on radar, communications, and advanced weapons systems. At an abandoned facility near Kogane, just outside Tokyo, they found the D-104 files. Inside, hand-drawn schematics, English translated notes, and pages of Japanese annotations that mentioned the words phantom signal modulation. Leading the inspection was Major Robert Whitaker, a U.S. Army engineer specializing in radio technology. He had been part of the team that worked on the APT-3 carpet jammer, a secret American device used aboard B-2 bombers to disrupt German radar. When Whitaker studied the Japanese notes, he reportedly muttered to a fellow engineer, "They understood more than we thought they did." The device the Japanese had reverse-engineered was, in fact, a derivative of the American carpet-to-radar jamming system, deployed over the Pacific in late 1943. But somehow, through incomplete wreckage and guesswork, Japanese engineers had recreated almost 60% of its circuitry, enough to grasp the fundamentals of radar deception. In post-war debriefings, American intelligence officers recognized the implications. Had Japan been able to mass-produce their own ECM systems, Allied naval radar and early warning networks could have faced major confusion during night raids or naval operations. It wouldn't have changed the war's outcome, but it could have cost thousands more Allied lives. The D-104 files were quietly shipped back to the United States and stored in the Wright-Patterson Air Force Base archives. Few knew of them and even fewer cared. But in the 1950s, a new generation of American scientists, working under Project Lincoln, the precursor to MIT's Lincoln Laboratory, rediscovered those documents. Some of the techniques described in the Japanese research notes bore a striking resemblance to the modulation strategies later used in ECM pods during the Cold War. Ironically, the ghostmaker that had once terrified Japanese radar operators became a building block for the next era of electronic warfare. In the years following Japan's surrender, the laboratories at Kogane were emptied, repurposed, and forgotten. The engineers who had once worked under the Imperial banner were scattered across a defeated nation. Some were drafted into rebuilding civilian industries. Others vanished quietly into the post-war chaos, their wartime work never to be spoken of again. Among them was Dr. Hiroshi Tanaka, the lead electrical engineer, who had first sketched the Ghostmaker jammer's waveform. When the Americans arrived to inspect his laboratory, he was nowhere to be found. His home in Setagaya had been destroyed during the Tokyo bombings, and the neighbors said he had gone north with his family before the surrender. Years later, a U.S. intelligence memo recorded a brief, almost dismissive note: Tanaka, presumed dead or untraceable. But the truth was more complex. Tanaka had indeed survived. He found work at a small radio manufacturing company in Nagano Prefecture, producing home radios and, eventually, early televisions. He never spoke about his wartime research, not to his colleagues, not even to his children. Only decades later, in the 1980s, would fragments of his life resurface. A Japanese historian named Kenji Morimoto, while interviewing retired engineers for a book on wartime science, stumbled upon an old man in his 80s who had worked at a secret facility in Kogane. When Morimoto asked about radar, Tanaka reportedly chuckled softly and said, "We thought we were building shadows." That phrase, "building shadows," would later become the title of Morimoto's 1991 documentary on Japan's forgotten wartime engineers. Meanwhile, across the Pacific, the American engineers who had studied Tanaka's work were already pioneering the next generation of electronic countermeasures. They built upon the same theories of wave cancellation and signal confusion that the Japanese had attempted, refining them into the sleek, modular ECM pods used during the Korean and Vietnam Wars. Yet not once, in any technical report or publication, was the name Hiroshi Tanaka mentioned. His ideas were buried under layers of secrecy and national memory, lost to both sides of history. In post-war Japan, public sentiment toward military research was one of quiet shame. Scientists distanced themselves from their wartime contributions, choosing instead to focus on peaceful innovation, the rise of Japan's new identity as a technological superpower. But beneath that transformation lay forgotten notebooks and sketches that once sought to outsmart radar beams, the same knowledge that had inadvertently paved the way for the world's modern stealth systems. The Second World War had ended, but the age of invisible warfare was just beginning. As the ashes of Tokyo, Berlin, and London cooled, two new superpowers emerged, locked in a rivalry that would span continents, decades, and ideologies. The Cold War wasn't fought with rifles or bayonets. It was fought with signals, shadows, and silence. And buried deep within that silence were the same principles that had once puzzled Japan's wartime engineers. The dance between detection and deception. By the early 1950s, the U.S. Air Force had turned radar jamming into an art form. Their engineers at Wright-Patterson Air Force Base were studying everything from microwave interference to synthetic aperture radar, creating machines that could scramble enemy detection across hundreds of miles. But what few realized, even within those labs, was that their new designs bore striking resemblance to the wave interference theory once tested in Kogane. A handful of the American scientists had seen the Japanese reports captured at the end of the war. They didn't copy them directly, but the logic, the foundation, the understanding of signal behavior lingered. a quiet inheritance born out of a defeated empire's final experiment. By 1957, the United States introduced the EB-66 destroyer, a flying fortress of electronic countermeasures. Its systems could confuse entire Soviet radar grids, rendering bomber formations invisible for brief, critical windows. The technology had matured far beyond anything the Japanese or Germans could have imagined in 1945. And yet, the physics behind it, wave reflection, resonance, and deception, were the same. What had begun as a desperate wartime experiment in a dimly lit Tokyo bunker had now become the backbone of nuclear-era strategy. In the Soviet Union, similar progress was unfolding in secret. At institutes in Kazan and Novosibirsk, Soviet engineers were racing to develop radar that could pierce through American jamming fields. It became a game of cat and mouse, one side building the beam, the other bending it. Each breakthrough, each discovery, brought the world closer to the invisible threshold, where detection itself became unreliable, and nations fought not for territory, but for information. Meanwhile, Japan had transformed. The laboratories that once built war machines were now producing televisions, radios, and semiconductors. The young engineers of the new era had no idea that their technologies, high-frequency circuits, wave oscillators, signal amplifiers, shared the same ancestry as their nation's wartime radar efforts. But history has a way of echoing through its own inventions. Every microwave oven, every wireless transmission, every satellite signal, they all shared roots in the invisible war. That began long before the Cold War ever had a name. In 1961, a declassified U.S. Air Force memorandum noted, "Some of the most fundamental theories of radar interference appear to have originated independently in both Allied and Axis laboratories during the 1940s. The convergence of these ideas underscores the universality of human innovation under pressure." It was an elegant way of saying what few dared admit. Even enemies could share the same dreams, the same pursuit of mastery over the unseen. And while America and the Soviet Union raced to cloak their bombers in silence, the ghost of Dr. Tanaka's wave machine lingered quietly in the background, a forgotten whisper that had once sought to make Japanese planes vanish in the night. By the late 1970s, the world's great powers had grown weary of the obvious. Missiles, bombers, and tanks had all reached their limits. The next frontier of warfare would not be about brute strength, it would be about disappearing. It was called stealth. In Nevada's desert, under the secrecy of Groom Lake, American engineers began designing a jet that could slip past radar like a ghost. The F-117 Nighthawk. Its shape was unlike anything seen before, jagged, angular, almost alien. But the technology behind its invisibility, radar absorption, wave scattering, electromagnetic cancellation, was not new. It was the culmination of decades of research tracing back to the war that had ended 3 decades earlier. Inside one of Lockheed's classified workshops, a physicist named Dennis Overholser studied ancient papers on radar theory. Among the notes, he found translated wartime documents describing wave confusion through multi-frequency interference. Some of these files had come from captured Axis research, including Japanese signal interference tests from 1944, the kind conducted by Dr. Hiroshi Tanaka's team at Kogane. Though Overholser and his peers didn't copy those ideas, they recognized something eerily familiar in them. Where the Japanese had once tried to hide planes from radar using brute force jamming, America was now doing the same through physics, by shaping the reflection itself. On the other side of the Iron Curtain, the Soviets were doing the same. At facilities near Moscow and Kiev, radar specialists were experimenting with absorption layers, coatings, meant to dull radar returns. They too had recovered and studied captured wartime materials, including fragments of Japanese radar jammers brought to Manchuria by retreating engineers. Unknowingly, both superpowers were building on the same lost foundation, the dream that Tanaka's wave machine had hinted at in 1945. But there was a deeper truth hidden beneath it all. The race for stealth wasn't just about machines. It was about fear, the fear that one flash on a radar screen could end the world. The fear that invisibility might bring power, and that power might bring annihilation. For every engineer who dreamed of bending waves to protect their pilots, another feared what would happen when detection itself ceased to exist. If one side became invisible, then deterrence, the fragile piece of the Cold War, would collapse. Thus began the paradox of the modern era. Humanity built machines to hide from its own inventions. In 1983, during a private interview, one retired American scientist, who had worked on both the ECM systems of the 1950s and the early stealth programs, was asked what inspired his generation to pursue radar invisibility. He smiled faintly and said, "We just followed the echoes. Everything we did was built on ghosts, the ghosts of war, of discovery, and of men who were never remembered." When pressed on who he meant, the man mentioned a rumor. A Japanese engineer in the final months of the war had theorized a method of redirecting radar waves through specific surface geometries, but his lab was destroyed before it could be tested. No one knew if the story was true, but in the world of radar and reflection, myths and science often blurred together. The Age of Shadows wasn't born in a single lab. It was born from decades of obsession, the desire to control the unseen, to dominate what eyes could not see, and to win wars before they were ever fought. From the British window chaff drops, to German Naxos detectors, to Tanaka's jammers and America's stealth aircraft, the thread of invisible warfare had woven itself through half a century of innovation. And in every hum of an aircraft, every pulse of a radar beam, and every whisper of static, there was still the same question that haunted the skies since 1945. Who sees first, and who disappears forever? The world today hums with invisible power. Signals travel through the air, unseen, untouchable, guiding aircraft, mapping oceans, connecting continents. Every second, billions of radar pulses, radio waves, and digital transmissions pass through us, tracing the fingerprints of an invisible empire built long ago. Most of us never think about it. We don't see the waves that define our reality, the echoes that once decided life or death. But if you listen closely, if you stand in the quiet between the static, you can still hear the ghosts of those who first tried to master the unseen. In 1945, men like Dr. Hiroshi Tanaka worked in silence, unaware that their wartime research would one day form the foundation of the modern world. They sought victory for their empire, but what they created instead was a blueprint for an age defined by signals and invisibility. Their ideas, crude, desperate, brilliant, found new life in the laboratories of the victors. From American ECM systems to Soviet radar arrays, from stealth bombers to satellite communication, the echoes of their work never truly faded. It is said that history is written by the winners. But in the realm of science, history is written by persistence, by the ideas that refuse to die. Even in defeat, innovation survives. Even when forgotten, knowledge endures. By the dawn of the 21st century, stealth had evolved into something once unimaginable. Aircraft like the Beta Spirit could glide unseen through storms, their dark wings blending into the night sky. Naval ships used radar-absorbent hulls. Drones circled the Earth undetected. And the same principles that once hid bombers now protected satellites, data links, and digital communications. In a strange twist of irony, the world Tanaka helped imagine, a world ruled by invisible signals, became one of peace and progress. The same waves that once carried war now carried connection. The frequencies of death had become the backbone of civilization. But there's a lesson buried beneath that transformation. Technology, no matter how advanced, always carries the memory of its creation. Behind every quiet triumph in science lies a story of fear, necessity, and survival. The invisible war never truly ended. It simply changed form. Where once nations fought to control the radar spectrum, now they battle over cyberspace, encryption, and satellite dominance. The battlefield is still invisible. Only the tools have changed. In 1998, a historian revisiting declassified Japanese documents at the National Diet Library discovered a single surviving schematic, the hand-drawn waveform from Tanaka's 1945 wave confusion device. At the bottom of the page, in faded pencil, was a note in his handwriting: when the world stops fearing what it cannot see, perhaps it will finally see itself. No one knows when he wrote it. Perhaps it was in the final days of the war, as the sirens echoed over Tokyo, or perhaps later, when he worked quietly in Nagano, watching his nation rebuild through the very science that once destroyed it. That one line, now preserved behind glass, captures the essence of a generation that built both horror and hope with the same hands. The legacy of the invisible war is not just found in stealth bombers or radar systems. It lives in the very concept of progress, the belief that knowledge, no matter how dark its origins, can evolve toward something greater. The war for invisibility began with desperation. It ended with understanding. And in between, it revealed something timeless, that even in the pursuit of power, humanity's truest invention was its ability to learn from its own shadows.